Hi, it's my pleasure to introduce this final session of the day. Firstly, I'd like to thank CBMM for hosting this excellent event, and also our colleagues at Beta Technology for all the arrangements that they've put in place today. We've had two sessions of really fascinating talks outlining how niobium battery technology is evolving. I think in this final session, we're going to step back slightly and take a higher level look at some of the opportunities there are for enhancing sustainability of raw material battery supply chains and enhancing UK but also international resilience around raw material supplies. Now, these are topics that are attracting a huge amount of interest currently in policy making circles, but also from the private sector and the research community. In a UK context, we've seen this clearly emphasised in several strategy documents during the last year. The first was the UK Net-Zero strategy, which emphasised the importance of critical raw materials in realising the energy transition, and also made a commitment to releasing a UK critical mineral strategy, which places a lot of emphasis on the importance of international collaboration, but also working collaboratively in an international context to strengthen supply chain resilience, and very importantly, enhance the sustainability, so the environmental, social and governance credentials associated with global raw material supply. So on that note, I'm going to introduce our first speaker this afternoon. It's Dr. Hadi Moztarzadeh, who's joining us online because he unfortunately couldn't be here with us today. Hadi is a technology and innovation strategist. He works for the Advanced Propulsion Centre here in the UK, and he's head of technology trends. And his work at the APC is very much focused around developing technology strategy, but also developing roadmaps to support the automotive sector in the UK. So he's going to talk about supply chain opportunities for the electrification of heavy duty vehicles. So I'll pass over to Hadi now.
Thank you very much. Thanks for the kind introduction. Good afternoon, everyone. First of all, sorry that I could not make it to be there in person this afternoon. Today, I was really looking forward to some face-to-face discussions and interaction with all of you, really. But given my son's flu and myself coughing and sneezing over the past kind of 24 hours now, I'm sure you didn't want me there. And apologies in advance if I had to mute myself for a few seconds during my talk. So thanks to all the organisers for their support, allowing me to do this talk online this afternoon. My name is Hadi Moztarzadeh. I am the new head of technology trends at the APC. Been with APC for just over 3 months now, and I'm going to briefly talk about APC and my department, technology trends. So let me just skip further intro for now. But let's just step back and remind ourselves why we are here. In 2020, transport sector accounted for 24% of the total UK greenhouse gas emissions, still almost double the amount produced by UK homes. It's down from 27% in 2019. And across the whole transport sector, automotive and vehicles obviously contribute most into this figure. So transport, specifically automotive sector, offers a significant opportunity to reduce UK emissions. The vehicle development cycle in the next 10 to maybe 15 years will affect our emission outputs for nearly a quarter of a century moving forward, when we are heading towards all of those ambitious targets for 2040 and 2050 for a net zero economy, global economy. The UK obviously has a very significant automotive supply chain, and the whole supply chain needs to continue to pivot into greener technologies if we are to keep our promises for a net zero transport and a net zero economy by 2050. And of course, if we are to maintain and grow industrial competitiveness and skilled jobs in the UK. So this slide outlines our role at APC to support the automotive sector alongside and I would say complementary to other funding and support mechanisms across the whole landscape. In the UK, we specifically support later stage R&D and commercialization through our CR&D program, that's our Collaborative Research Development Program, and Automotive Transformation Fund, which is the key engine, I have to say, to develop upstream supply chain for the future of automotive sector, specifically for batteries, power electronics, materials. We also have some bespoke funding programs like for SMEs and for other development processes like demonstrators. So we support the sector across these 7 strategic technologies by understanding and running various programs of work around these 7 key technologies for the automotive sector. My team at APC, Technology Trends team, directly deliver the 3 on the left-hand side of this slide, the technology roadmaps, the Automotive Council roadmaps, and we provide strategic inputs and strategic insights, now quarterly demand report. You probably have seen some of them over the past 3-4 quarters to inform basically decision-making process and investment plan across these strategic technologies. We also do and undertake and provide bespoke analysis on key technologies, mobility trends, and all of these feed into our major funding programs, CR&D and ATF I mentioned earlier, also supporting national and international events and conferences like this one today. Now let's take a look at the HDV sector, and my argument here is mainly applicable to HGVs, heavy good vehicles. I mean, I have not included off-highway duty vehicles, heavy duty vehicles into this presentation. We are working on that segment too, working on the TCO model and likely powertrain solutions across the whole HDV sector. Planning to publish an insight paper on HDV decarbonisation, hopefully Q1 next year, to include both off-road and on-road heavy-duty vehicles. But for now, the main assumption here is on-road HGVs. So bear that in mind when I'm talking through the next 3-4 slides. So in terms of vehicle classification for heavy good vehicles, we have these 3 broad categories, 7.5 up to 18 tons, usually called medium duty vehicles, MDVs, used for local distributions. Then the next one is 18 tons to 26 tons, typically referred to as heavy duty, mainly used for local distributions and heavyweight utilities. And then anything going above 26 up to 44 tons trucks, also called heavy duty, for high payload distributions and containers, and they normally do cross-continental travels and transport. Then from our roadmaps for HGVs, we outlined potential pathways for decarbonisation of the HDV sector. Here we are looking at the 2020 to 2050 timeline, bearing in mind the 2 key policy transition dates currently mandated by EU and UK. So we are already seeing some BEV solutions for MDVs, and following some successful trials of fuel cell, I think we will see fuel cell solutions too, probably by the middle of next year. There are some commercial applications already in Europe, I think, and for the heavier trucks and long-range trucks, we are already seeing some potential BEV and fuel cell solutions. There are still a lot of discussions at industry level and policy-making level about the use of hydrogen internal combustion engines as a transitionary solution, or maybe a longer-term option, subject to green hydrogen supply, obviously. But again, I think it's clear that BEV and fuel cell at the smaller scale will play the main role for the majority of the heavy truck requirements. So we have developed a TCO model for these different technologies, so these different options, and now we are looking at 2035 to 2040 kind of horizon. On this slide, based on that TCO model, we believe there are 4 main options to decarbonize HGVs, and actually it applies to the whole of the HDV sector, so construction vehicles is included here, as you can see on the top of the slide. So I believe 2 main horses in the race to zero emission HDV sector will be electrification and fuel cell. Which means moving from today's profile of more than 90% of the fleet being internal combustion based on fossil fuels to around 62% diesel in 2030, and then a major shift we will see from 2030 to 2040, getting to more than 70% of HDVs being on BEV and fuel cell technologies. And in that mix, you can see battery electric will be dominant of around 40%. So having that in mind, now let's take a look at one of our recent publications, our latest quarterly demand report. It's the latest one until next week, or maybe the first week of January, when we publish our next quarterly demand report for Q3. This one is published in September, and you can download it for free from our website. I have to add that in previous quarterly demand report, this one and the next one we're going to publish, as I said, either next week or the first week of January, we did not do a specific analysis for the HDV sector demand yet. We are currently doing a supply chain mapping and intend to publish an insights report based on that, and then provide detailed analysis of the battery demand, including alternative chemistry and some of the discussions you've had today from the previous 2 sessions. So just have it at the back of your mind while I'm talking over the next few slides. So this is an overview of what our quarterly demand report covers from global, European and UK perspective. Our forecasts are based on vehicle production geography rather than sales. And we look at LDVs, light duty vehicles and HGV vehicle segments in our quarterly demand report. So we analyze the materials requirements, also forecast electric motor demand and materials requirements for that too. The background context for the quarterly demand reports, specifically for the latest one, comes from this illustration of the growth in the UK battery demand from 4 gigawatt-hour in 2021 to almost 100 gigawatt-hour in 2030. And you can see the production and supply is still way below the forecast demand in 2030. This is only for the UK. And on the next slide, I'm going to show you the latest forecast for automotive sector battery demand at global stage, European and UK. So this is basically the forecast for automotive sector battery demand relative to 100% BEV ceiling, which assumes a scenario where all vehicles produced are battery electric. We see the expected growth in global battery demand in this decade is only the start, I would say, and we expect there to be more than 3,000 gigawatt-hour demand in the 2030s. European demand is expected to be accounted for around 1/3 of global demand in 2030, and UK demand, as I mentioned, would be around 100 gigawatt-hour by the end of this decade. So the next two slides, this one and the next one, are focused on LDV segment. As I said, we didn't do a tailored HDV analysis last round, and even this round, we are not going to provide detailed data for the HDV segment. As I mentioned, we are working on an insight paper on supply chain opportunities, and we'll provide detailed data and figures for the HDVs. However, I think looking at the battery demand from LDV perspective will give us a good overview for the supply chain opportunities across the entire supply chain. And I'm going to mention some of the cross-cutting themes and challenges and opportunities for the whole sector for all vehicle segments. So bear with me until I get to those summary points. So battery demand for LDV segment, passenger cars and vans under 3.5 tons accounts for more than 85% of the total automotive sector demand. And as we expected, BEV production takes the lion's share of demand out to 2030. Globally, we expect BEV production accounts for around 40% of all cars and van production by 2030. And in Europe and the UK, we see this figure being above 60% in the same period. Relative to our previous quarterly demand reports, I think we will continue to be revising these figures upwards in line with increasingly ambitious, I have to say, electrification targets by both governments and policymakers and industry around the world. Especially other vehicle segments like HDVs and other applications like stationary storage will add up to these figures significantly moving forward. The massive growth in battery demand, in lithium-ion battery demand, naturally goes hand in hand with the need for battery-grade lithium supply, feeding the thousands of gigawatt-hour worth of cell production. So looking at the numbers in lithium carbonate equivalent, we expect global lithium demand from passenger cars and vans to be near 1.8 million metric tons by 2030. And this is based on a conservative battery pack sizing assumption relative to other forecasters. This figure, I have to say, could be much higher if we increasingly make more BEVs with larger battery packs as decade progress and as most of the OEMs are moving towards that at the moment. So I think overall, compared to demand last year, in 2021, the lithium needed for BEV production expected in 2030 would have to be like 8 times higher than the amount we are producing. We produced. It will be 8 times higher in 2030 compared to 2021. So we identified some of the solutions and some of the potential scenarios to reduce reliance on lithium to address potential lithium shortage in 2030. In the short to medium term, we identified these 5 main levers. While there has been a lot of talk about the investments required in extraction and refining of battery-grade lithium, in our latest report, we focused on understanding the potential demand side from OEMs, and it's LDV OEMs I'm talking about here. So those scenarios on the right-hand side, decreasing lithium demand is mostly applicable to LDVs. But I think on the next slide, I'm going to show you some of the impact that the HDV OEMs requirements and strategies could make to address them as well. So just going back to those pathways to reduce exposure to lithium shortage, based on our analysis, the impact of investment in lithium extraction, sustainable lithium extraction, and basically investing in upstream supply chain for lithium could be relatively high by 2030 compared to recycling lithium from BEV, for example. We think this significant supply from BEV, end-of-life retirement, the recycling of batteries, will likely come after 2030, maybe around 2040. But obviously investment and innovation in recycling should happen by the end of this decade, and we have to think about it upfront to enable recycling towards the middle of the next decade, towards 2040. In terms of decreasing lithium demand, moving to a smaller battery pack could have a relatively high impact, mainly applicable to LDV segment, and it would call for obviously more investment in charging infrastructure, which could be a helpful step forward for the electrification of HDVs too. Looking at alternative chemistry, we said it could have a lower impact, again, mainly because it's still at R&D stage. Moving towards higher TRL and MRL levels would probably take slightly longer, would happen probably after 2030 to have a bigger impact. And the other scenario for both LDVs and HDVs is combining and using alternative net zero powertrain technologies, like using fuel cell technologies alongside battery electric technologies. We also identified some of the cross-cutting challenges for the battery innovation for automotive sector. LCA consideration, we covered that in our report. Emission targets, recycling mandates, eliminating harmful chemicals during the battery production. They're all pushing and pressurizing all companies to improve the environmental impact of their battery production and usage. Manufacturing improvements. Lithium-ion manufacturing has focused on scaling up to reduce costs over the last few years, and the next phase will probably see innovations that optimize existing manufacturing processes to reduce cost and to improve performance. Safety improvements, as more EV battery cells are placed on the market, enhancing safety has become a high priority. Despite ever improving manufacturing processes, the risk of onboard cell failure increases as EV volume rises. So to avoid costly recalls, most of the OEMs are paying more attention to using safer cells, and I think they're even ready to pay a premium for safer cells. Different solutions and innovation to reduce likelihood of thermal runaway events are being considered and being investigated. So that's another area. And supply chain vulnerability and resilience, increased demand for all of these critical minerals, nickel, cobalt, lithium, driving up prices in the short to medium term. Alternative chemistries that are made from more abundant and cheaper materials like LFP and other materials. Niobium was being discussed today. It's an expensive material, but it could provide an alternative chemistry for high power, fast charging requirements. And these kind of alternative solutions and having different options is a way forward, we believe. So, in summary, I think the global battery demand growth for this decade, reaching over 2,900 gigawatt hour by 2030 for the automotive sector. And this will, of course, putting pressure on global lithium supply, which needs to grow exponentially by 8 times compared to the current level. And we need to invest more in battery innovation for different applications. Invest in alternative net zero technology, powertrains technologies, alongside BEVs to reduce reliance on one materials, to reduce reliance on lithium markets. Also, EV batteries will be subject to cross-cutting challenges, which calls for R&D and innovation across these 4 themes. I talked about safety and manufacturing improvements and recyclability and implementation of a circular economy business model, and of course supply chain development, especially on the upstream side of the battery manufacturing and battery supply chain. That's where we need to establish links with likes of CBMM to ensure security of supply for the future of UK battery demand. So UK opportunities in this sector: developing upstream supply chain, attracting anode and cathode manufacturers to build an ecosystem for battery production here in the UK. Also investing in recycling batteries to build the infrastructure required by 2030, when we will see end of life for some of the current EVs, and R&D investment for alternative chemistry for different applications to reduce reliance on one material. I think we had the news a few weeks ago. We have confirmation of the second round of funding for Faraday Battery Challenge, which will leverage R&D to address some of these battery innovation requirements. But obviously, we need continuous investment, private and public investments, to secure the future of the UK automotive sector. And here are the next 3 insight reports we will publish in the next 3 to 4 months. Just to reiterate that you can download all of our insight reports, roadmaps, thought leadership pieces, including the one I have covered just now, from our website. And if you needed any further details, please feel free to get in touch. Thank you very much.
Hadi, thank you very much for an excellent overview of the implications for particularly lithium demand, which everyone is generally fairly conscious of, given projected uptake for electric vehicle sales globally, but also placing that in a UK context. Just on a very relevant note, my colleague Evie and I are actually hosting a UK lithium supply chains workshop in London tomorrow, and APC are also attending that. So we hope to engage with them further on that important topic. So moving swiftly on to our second presenter, we've got Professor Joe Dewulf here from Ghent University in Belgium. He's going to be talking about environmental sustainability and assessment of niobium production. Joe is a professor of clean energy technology at Ghent University, and he leads their sustainable engineering group. So I'll hand over to Joe now, who's going to cover this topic in the next 20 minutes or so. Thanks.
Good afternoon. Thank you for the intro. Thank you, the organizers, for the nice event, interesting event, and also for giving me the opportunity to present a bit of our work. The work I did together with Lydia. Lydia is working in Ghent, but she's Brazilian, so that makes a kind of a link. I have 3 sections in my presentation. Very broad, I will talk about raw materials and sustainability first. Second, I will indeed look into niobium, and then I will end up with conclusions and perspectives. Raw materials, well, they are very high on the agenda, and it has all to do with a transition we undergo. We need to harvest renewable energy. We need to transport it. We need to store it. So it's really becoming more and more essential, these raw materials, for this energy transition. That's very obvious. So it should help us in addressing climate change in a way or another. The need is huge. If you look to international reports, for instance, from the OECD in their outlook to 2060, they expect a quadrupling of demand of metals. And if you look to the European Commission studies towards 2050 for nickel and cobalt, they expect a 3-fold or even a 10-fold growth in demands. That's huge. So circular economy and the recycling will not be able to supply the demand. So we will need further virgin resources, I may say. And this, of course, they are essential, these materials, to address climate change. So they should mitigate climate effects. But of course, these huge amounts of materials, we may wonder if this will be also with a certain footprint or a new footprint or another footprint. So are we really facing a sustainable transition these days if we have these huge amounts in front of us that we have to mine, refine, process, manufacture, and so forth? So we need a kind of sustainability assessment, I would say. And it's very important because there are already some potential threats in scope. We know that mining, like agriculture, is a land-based activity that brings threats for biodiversity, for the ecosystem. And we know that we also need ecosystems because the ecosystems provide us with ecosystem services, provisioning of food, regulating services, cultural services even. So pretty important. And in 2019, the United Nations, apart from the IPCC panel, they finally also had a panel on resources, I would say. And they came up with their first report in 2019, and main conclusions were also translated in the broader media, where you see that, okay, extraction of the natural resources cause 80% of the biodiversity loss, according to that study. And if we are going for a 4-fold or a 10-fold extraction, we may wonder what this will bring in terms of biodiversity impacts and others. So we need a kind of sustainability assessment. Are we creating a new problem by solving another problem? If we look a little bit into the sustainability assessment toolbox, well, essentially, we should address the 3 pillars of sustainability: people, profit, planet, environmental, economic, and social. And if you look to the core of that toolbox, we have social tools, we have environmental tools, let's say, and economic tools. And in the center, you have LCA. And to my experience, to my insights, this is the most advanced one in addressing the different sustainability assessments. They all are based somehow on life cycle thinking. I think this is crucial that we have really a perspective on the full value chain, from mining to the recycling and so forth. And of course, there are also other methodologies accounting for supply chain issues. For instance, criticality is coming in there. So coming back to the environmental pillar, let's start with that. Well, it might look, this LCA, pretty new to you, but essentially it's not. It dates back from the 80s in Switzerland somehow, the first work. And in policy, about 20 years ago, you had the insight at the European Commission that LCA might be one of the best frameworks to address environmental impacts, assess environmental impacts. Already 20 years ago. So in the European Union, a lot of research has going on. Also with industries the last 10 years, I would say. And today we have a kind of product environmental footprint. The PEF you might be familiar with, which is somehow a standardized way of LCA within the European Commission, heavily supported by the Joint Research Centre, the EPLCA over there. Sustainability is not only about environmental issues. Already today, other speakers have mentioned social issues, especially with cobalt. We have issues, so that's also something not to be forgotten. And of course, there is also the social aspect, the economic aspect. Criticality or resource criticality of critical minerals. Well, there are different methodologies there in the US, in Europe, and now I see also in the UK this year a lot of activity in this sense. But essentially, all methodologies that I analyzed some time ago, they all come back to 2 important aspects. If there is a certain level of economic importance and if there is a potential risk of supply disruption, if we are in this upper quadrant, there we have the positioning of the critical raw materials, but whatever the calculations are behind, but these are the 2 core principles behind. And if we look to critical raw materials for the European Union, this is the latest list in 2020. So we have every 3 to 4 years an update of the list. This is the latest list, and you see here that we rely largely on China, but also other countries, and for sure also niobium is in the picture with over 90% of niobium supply to the EU from Brazil. Just for information, in the European Union, we are also working in expanding the product environmental footprint. So that means that the European Commission on the long term likes to move from product environmental footprint to product sustainability footprint. That means that we like to expand from the environmental pillar, also incorporating social economic issues, but even circularity and criticality making up the full, let's say, picture of product sustainability footprint. That's an ongoing project with multiple partners, as you may imagine, industry included. That brings me to my second section, looking into niobium. So we had a recent study together with CBMM, quite important if we like to address sustainability or environmental sustainability, at least of niobium raw materials. So we looked into niobium oxide production, and we wanted to identify environmental hotspots and also to see room for improvement, options to improve the production. So this year the paper has been published with Lidja as the main author. I will explain a little bit of the outcomes there. If you have interest in further details, you are welcome, of course, to look into the paper. So essentially what we did is a cradle to gate. So we looked to the niobium oxide leaving the plant over there in Aracha, Brazil. And we all related all impacts to 1 kilogram of niobium oxides. Here and there we need to do some allocation. So these are some things you need in an LCA. We were lucky to have, let's say, really representative data from the company, primary data, as we say. And of course, for the background supply of chemicals and so on, we need to rely on market supply. And there we have, let's say, a databases like from the eco-invent we used. We looked into different environmental impacts. Here in the presentation, I will focus on global warming. And of course, you need some software to run that. So here you have a scheme with the main processes included into the system boundaries, the mining, concentrating, refining, the oxide processing, and of course also attention for the further downstream processing of residuals, the tailings, wastewater treatment, and so forth. And of course, you have inputs that you take from nature, but also from the market, as you say, chemicals, for instance, for the processing. And you end up, for sure, also with emissions next to your main product and co-products. Before I look into the results, I think very important is to look in what we call the so-called life cycle inventory, the ins and the outs, the inputs and the outputs to your process, because in the end, they are going to determine your footprint, right? We looked into 2 production years, 2017 and 2019. So you have the 2 columns over here. And here, it's not a full table with everything, but let's say a couple of key flows. Of course, your ore body, remarkable is that the amounts we needed in 2019 or CBMM needed in 19 were higher than in 17, so ore grade was different. That's what you understand. That was not really favorable in terms of decreasing the footprint in time. However, there were a couple of other factors that were favorable. For instance, the introduction or the use of renewable energy was increased from 17 to 19, and the non-renewable based electricity was even phased out in between 17 and 19. Then also with respect to the consumption of fuels, as you see here, different points, we also have seen even that a lower ore grade was used. Even there, we saw a reduction in consumption because of process modifications. If we utilize this information and other information and we calculate the carbon footprint in kilogram CO2 equivalents per kilogram of niobium oxide, we see a reduction from over 6 down to 4.7 in between 2017 and 2019. Well, if I concentrate on 3 main contributors over here, first of all, we have the direct emissions, that is the red block. Despite we had more ore in 2019 and 2017, we observed especially lower amounts of coke, petroleum coke, diesel, LPG, On the other hand, we had more charcoal used in 2019, making up, let's say, or contributing to these direct emissions. On top of that, the yellow block, in terms of chemicals, we have also a mixed picture here. We have more potassium hydroxide used, but far less sodium hydroxide and sulfuric acid. So also somehow contributing to a decrease in the footprint 2019 versus 2017. And then the energy mix, the green, that's let's say the most different one, or the one with the highest difference in between 17 and 19. Especially because we have in 2019 this full renewable-based electricity that contributes to the reduction of the carbon footprint. So overall, it's about a 1/4 reduction in between 2017 and 2019. You see that process improvements, they really matter. And that's a result of different contributors, I would say. The electricity mix has been changed, the chemicals, the fuels, fossil fuels have been changed, chemicals as well. Following the raw materials production, of course, you are not yet at your final product for your client. We have to look into the next stage, which is the manufacturing of materials. And there we have an ongoing study with Echion, and the study is available, but the publication is underway. I suppose Alicia is working on this afternoon. Well, we looked to this niobium-based XNO, as we already have seen today in another presentation, and compared it with the LTO active material. And if we look to the carbon footprint again, well, we see about 50% less carbon footprint associated with the XNO material on a mass base, kilogram. And if you also factor in, let's say, the performance, if you look into the cycle life, the kilowatt hours delivered over the cycle life, you see even a higher difference in the sense that, yes, about 40% is the footprint in terms of the XNO based battery material compared to the LTO based one. So in this sense, it looks that the material, the battery material here is pretty promising also in reducing the carbon footprint of battery materials channel. So that brings me to my third section, conclusion and perspectives. First of all, I think it's very important that companies go on with process improvements. They really matter. And it can be a contribution of everything, I would say, in supply chain, the energy mix, the chemicals. They all contribute, and they can contribute significantly, as we have seen in the comparison 2017 versus 2019. If you look in the niobium oxide production, I think the processing chemicals, they are still important, and that's a bit upstream of the facility. So that's also something important for companies. Also look into your supply chains of chemicals and energy, because also there might be still gains you can make. I think in this sense, yes, I would not say that CBMM or other companies should stop with the 2019 results. No, they should go on in looking for process improvements, and also in not only their own process improvements, but also in their sourcing of chemicals and so forth. And from the results we have so far together with Echion company, it looks like that the niobium-based materials is quite promising from environmental perspective, the carbon footprint perspective. Some perspectives next to the conclusions. I think these raw materials, niobium and others, they come with a footprint anyhow. We need this mining, refining, there is a burn anyway, there will be impacts on biodiversity and so on. So my point is that we should try to minimize that, of course, with optimization of the supply chain, but also the end of life. Once we have these precious materials, I would say, we should keep the value in the economy. Yeah? It would be a shame to use them once in a battery and then lose them. So we have to keep the value And that's something I worked on during my stay at the ETH in Zurich because people in the LCA community, they think that we have to address resource depletion, that metals disappear, but they do not disappear, of course, you know that. But what is the issue then with metals and metal supply? Well, actually, to my understanding, we need to keep them accessible for the next use, for the next life cycle, for the society on the long run. And I think that's the challenge as a base to, let's say, develop circular economy, because I think that's the way we should try to keep the value in society, that the investment we have done economically speaking, but also environmentally speaking, that we have return on. So end of life management is very important, and not only at the end of life, I think at the design, it's pretty much important. And then people immediately think on recycling. I would say yes, but also no. If you go into literature for circular economy, you will find more than 30 R words, from repurposing to reuse and whatever. Of course, they do not all fit to battery materials, I do understand, but it might be more than just recycling as well there. And for the future sustainability assessment, of course, we should look into the carbon footprint, global warming, but it's much more than that. First of all, environmentally speaking, ecosystem services impacts is important. It's not properly incorporated in LCA, to my understanding today. So we really have to bridge with the community working on ecosystem services impact assessment. And as I told you, there's not only people, there's also not only planet, there's also people, also the social impact assessment is important as well. So that was my presentation. Thank you for listening.
Thanks very much, Joe. That was a really useful overview. It's a good context about the importance of taking sustainability criteria into account when we're looking at supply chain resilience, with a really nice case study there, focused on on the material of the day, niobium. So I'll be interested to look more closely at those papers you published on that topic. So we're moving on to our final speaker. I should have said at the start that we're going to have a bit of a question and answer session after this. I think Hadi is still on the line, so we'll be able to take any questions that are relevant to him or his presentation after this final presentation from Alexander Thompson. He's from European Metal Recycling, based here in the UK. He's the Innovation and Project Manager at European Metal Recycling. And he's responsible for leading the RECOVAS consortium, which is a significant project which is focused on developing a circular battery supply chain within the UK. So I'm going to pass over to Alexander now, and he's going to talk about developing this new battery supply chain in the UK.
Good afternoon. Nice to see all of you here. It's quite fitting really that I have the final speech of this, because we are looking at what happens, the final stage of the battery when it reaches its end of life. So RECOVAS is an Innovate UK funded project through the Advanced Propulsion Centre. So it's a 9 consortium group. So we've obviously got 3 big OEMs in there. We've got a company called Connect Energy, who do static energy storage systems, looking at repurposing batteries at end of life. Warwick Manufacturing Group, who I think we have represented here as well. Who else we have in our UK BIC? I think we've already heard from as well this morning, so you're aware of. Autocraft look at repurposing of batteries. HSE, we're all aware of, and EMR. So this is the one that sort of explains what we all do as part of this project. So over here, this is where the vehicle reaches end of life. It's coming into the recycling centre. So EMR at the minute process electric vehicles at 60 sites in the UK, with the largest end of life vehicle recycler. When we get the electric car in, we obviously need to safely store that vehicle, particularly if these have come in as accident damaged vehicles. So looking at triaging of that battery pack once we've taken it out of the car to assess whether or not it can be remanufactured to go back as a traction battery, whether or not it's still got a reasonable state of health, in which case it can go into a static energy storage system, or failing those two, we have to start recycling it. Obviously, that falls into two aspects. So we primarily take these batteries and we disassemble them down to module level, and those battery modules, they go into a large nitrogen inerted shredder to break down the battery cells and the modules all the way down. So you cover your aluminiums, your coppers, your plastics in a small pelletized form, that sort of size, and then your black mass, which will go to a refiner. So your black mass is everything that was on your cathode and anode, all of your coating materials, which is where all of your high value metals sit. And obviously niobium in the future would come out in that stream most likely. That obviously then circles round to your manufacturers, to your gigafactories, back to your OEMs. So why does this project exist? At the minute, OEMs have large liabilities for these batteries at end of life. We need to try to reduce that liability down to zero so they don't have it sitting on their books. Also, the last owner of the vehicle has a positive asset in that battery when they're coming to scrap that vehicle at the end of its life. Critical resources, as has been identified and discussed, most of these materials are imported. We need to make sure we retain what we have in the UK to be able to feed the supply chain moving forwards. So a little bit about EMR, fairly big business, probably haven't heard of us. So 100% family owned still, 6 billion turnover last year, processed about 10 million tons of material. And it's said, largest end-of-life vehicle recycler in the UK. We've got 60 sites. We're talking 20, 30,000 vehicles a month coming through the facilities. So this is our site that we have in the US. It's in effect a reverse assembly line. So when we're getting these cars in, we're identifying between 10 to 30 target components. So we're pulling off these vehicles to be able to feed back into the green parts business as second-hand reusable parts on these vehicles. This is where the batteries will come out. We're building a similar setup in the UK at the minute. So Recovast has been going for just over 18 months now. EMR have learned a lot in that time. 18 months ago, we were seeing 1 or 2 EVs coming into the business, mostly early Toyota Priuses, the occasional Nissan Leaf, but really low volumes, and it's something the industry wasn't particularly looking at. In short, we have to process them very differently. That's from goes from your receiving the vehicle in the first place throughout the entire process. There are very few aspects which are actually similar, and it's going to be a big transition for our business moving forwards. So currently, body, wheels, subframes all stay fairly similar. We can use our traditional recovery process for looking at those, but other than that, it's all different. The battery we obviously know about is quite high profile, and we're talking about also things like the drive motors. They're big, expensive units that tend to actually outlast the vehicle. So looking at potential reuse applications. They also have rare earth magnets in them, which is one of the other critical resources that we're looking at from a UK perspective. ECUs, the battery management system, is getting bigger and more complex. You've got some very high value kind of PGM type materials in there. You're looking at recovering as well. And the high voltage wiring, there's a significant copper content in these vehicles. Copper's trading around £10,000 a tonne type of price. It's a worthwhile resource. We need to keep it in the UK. We need to recover that as effectively as possible. The other thing to consider, we're doing this now, but we're doing it now because we know we should, rather than because the business case is there. Similar to some of the graphs you may have already seen, but as you see, we are about here at the minute. So even now on the new car sales, the total of internal combustion engines is still exceeding all battery vehicles, and that's going to obviously change fairly rapidly as we get towards 2030. However, this is the interesting one. When you look at the end of life, you've got about a 15-year delay and lag between them. So when we're looking at current volumes, we're talking almost negligible volumes in comparison. So we're not doing this because it makes commercial sense at the minute. It's not until we get to about 2039, 2040 that we as a business will start to see a 50-50 split. Up until then, it really is about developing this infrastructure and building it in a scalable way moving forwards. Then this is the lag between the number sold and number reaching end of life. And this is where the circularity falls into challenges. We also know with the evolution of battery chemistry that the vehicles being placed on the market today are going to have different chemistry to what the vehicles being placed on the market in 15 years time are. So even though we can recover those materials, they're not going to be the exact same materials you want to feed into your vehicles of the future. So it's about how we can bridge that gap, fill that gap, as was mentioned previously. More raw materials will need to be brought in, but we need to make sure that we recover the materials that we do have because of the strategic importance of that and the value in them. Other one, as discussed, massive variety of things. So from our side, we're looking first at training of operatives. Traditionally, the end-of-life vehicle market, vehicle breakers, is not a high-tech industry. It's not highly skilled workers most of the time, and these are really dangerous batteries that they're dealing with, dangerous environments. So there's a lot of training and skills that are being needed brought into this space. Again, standard operating procedures, how you deal with these vehicles. As a market leader, it's part of the MR's responsibility to write industry white papers and share this with the wider sector, because if we don't do it, others won't, unfortunately. And the key one at the minute for us, so trying to build up a database of what chemistries are in all of these battery packs, what configuration they're in, moving more to cell to pack level rather than modules. It obviously changes what you can do from a reuse or repair perspective. But the key one for us is understanding the chemistry. Huge part of that is about the value of it, what your nickel, manganese, cobalt content is, etc. But also moving more towards some of your future battery technologies with the LFPs, LMOs, etc. Your values are changing significantly, and that hugely impacts the value of that vehicle at the end of its life. Other one. It sounds obvious, but dismantling these batteries and then shredding these at the end of life generates some chemicals which you wouldn't necessarily expect in the first place. So you've got fairly obvious ones, so like fire risks, which is why you tend to either shred these modules wet or in a nitrogen inert atmosphere. Flammability from the electrolyte, as was highlighted previously, there's massively varying chemistries in the electrolyte as well. So you can't just assume a single flashpoint for these types of materials as well. Other one, graphite. As we all know, it's incredibly fine dust, so the explosion risks are huge. You're having to have incredibly high levels of containment. Pharmaceutical grade equipment is what we're mostly putting into our plants, running at negative pressure in order to try to achieve that. And the other one on the chemical safety side of it. So all the carcinogens, the sensitizing metals, and also HF gas has been a huge discovery that I think is not very widely spoken about in the battery recycling sector in particular. But the generation of those types of gases that you have to try and manage and deal with and scrub out and clean during your process. There are some fairly scary videos when you look online at what's being done in the Far East and Asia. You see plants covered in black dust, which is obviously half graphite, but it's also half some of your carcinogenic metals. And in the UK, we need to make sure that we are the complete opposite of that, and we're doing it right from the start so that when our volume builds in 10, 15, 20 years time, we're doing it in the right way. But the key one is looking at the processing of it. So it's discussed, yeah, we need to go massively high grade from a processing equipment side of things. The other one, so looking at personal exposure monitoring. So it's why we're working with HSE. So looking at personal exposure limits via kind of blood and urine testing for some of our operatives as well, and making sure that feeds in so that we have evidence that the procedures and processes we're putting in place are working as intended. And again, things like the PPE, what's widely available on the market doesn't necessarily align to what we found you actually need in this space. Other ones I mentioned, things like LFP and new materials coming into batteries. The whole point of this conference in the first place is these chemistries are changing. There's a lot of aim to take out some of those expensive materials in it. From a recycling perspective, that obviously massively changes the commercials of it. We expect we may get back to a point where we are almost now, where we have to charge a gate fee to process these materials because there's so little residual value in the packs. So it's a really interesting market dynamic that we expect it to go positive, but it will then slip back as time goes on and chemistries change. So that's one of the other ones, why we're looking at graphite, electrolyte. At the minute, they're mostly considered a waste product. Battery grade graphite is incredibly expensive to produce in the first place, and at end of life, we have a disposal cost of £100 a tonne. It makes almost zero sense for that to be the business case. So looking at ways that we can reprocess that graphite and recover that material is key to it. Again, electrolytes, similarly, the minute they tend to be burnt off as waste, but we need to be able to look at meeting those recovery, as well for the EU directives coming in for recycled content targets. So that's the next stage for EMR as a business. So looking at how we can recover the graphite, do we do it wet or dry processing? There's a lot of conversation about hydrometallurgical versus pyrometallurgical processing, particularly for the black mass. But how the primary processing and shredding is done has a huge impact on what downstream processes can be done to the material, what the most optimized flow sheet looks like for that integration between the primary processing and the refining. Key conclusions so far. Very different to recycling ICEs, more so than we initially expected as a business. You think of it, the batteries different, the rest of it is largely similar. But even the construction methodologies and techniques that the OEMs are using with their EVs, we're seeing already starting to change. And when we're looking 10, 15, 20 years down the line with them, we're seeing drastic changes in the maker of the vehicles with them. So the volumes are coming, but not yet. This is why it's commercially difficult for people to set up as a battery recycling or particularly on a refining process in the UK. And that's what the challenge is. As a family-owned business, we have the option and opportunity to build small and to start that process. But realistically, if you're coming into this as an outsider, it's very, very difficult to justify anything looking at end-of-life volumes for another 10 to 15 years. And it's why anyone coming into this space is so focused on production scrap contracts, which makes sense in a way, but equally, we should be working with the gigafactories to help reduce their scrap rates. And that should be the key focus rather than recovering the material that comes out of them. Huge variety of packs is the other one, as I said. And yeah, the LFP. So cobalt, nickel's not enough. We need to focus on all the other materials coming through. It's one of the things about niobium. At the minute, I don't think anyone's really looked into understanding how this would be pulled out in the waste streams. So which, during the kind of traditional leaching process, how it would be recovered in that, whether or not it makes sense to pull it out dry before you get in the same way that we separate and recover the graphite, and what the opportunities are there. Obviously factors into the design process as well. So making sure that we consider that circularity when we're designing in the first place, and we think about how we recover these high value materials as well as possible. That's all from me. Thank you very much.
Thanks, Alexander. That was a really useful overview of some of the challenges associated with electric vehicle recycling and the recovery of the valuable raw materials that they contain. But it's really good to see that companies like EMR are undertaking the research and making those investments now to hopefully be able to realise the opportunity 15 or 20 years down the line from now, which is really the reality of what has been shown today and what you described. So that's the end of the presentations. We've got about 15 minutes for any questions. So if you've got any questions for Hadi, Joe or Alexander, please call out. or on that matter, if you've got any general questions that you haven't had an opportunity to pose today, please feel free to come forward with those.
Okay. My question is, so when you consider the recycling of these metals, everything, so in terms of supply chain, is there any prediction like what would be the supply chain after second life usage? Whether if you're taking lithium need about 60 kilotons in UK, say if you're considering second life of batteries also, is that considered in your predictions, or is there any sort of predictions happening if you consider second life also? What would be the supply requirements across UK or Europe?
I could certainly say in the context of the work that the British Geological Survey has done around this topic, we've done some analysis about future opportunities for recovery of material from recycling funded by the Circular Transport Plus network, and we've certainly considered the lag that arises as a result of incorporating the second use applications for energy storage, grid scale energy storage technologies, for example. I don't know if Hadi wants to come in on whether that's included in APC forecast with regards to when battery raw materials might come back into circulation.
I think I mentioned during my talk that we expect it to be after 2030, probably halfway through the next decade. And I have to be honest, because of that, we haven't had enough investment in the UK for recycling and for circular economy business models and the underpinning business model and finance model for recycling of battery materials. So we are looking into it now through ATF. Recycling is now one of the high-level themes, and I think it's becoming more and more important for the whole UK automotive supply chain and Europe. Europe have done some investments, and they are now moving towards establishing some of the infrastructure required for that purpose. And we are planning to do the same here in the UK, hopefully. But yeah, just go back to the question. I think it will be after 2030 when we see end of life and retirement of some of the current BEVs and EVs.
And I suppose just maybe Alexander might want to pick up on that. Are you taking account of that in terms of your projections for when some of these flows might enter into the market to be recycled?
Yeah, so it's obviously factoring. Yeah, it's obviously factoring quite heavily into our models. It's one of the interesting things about the new EU batteries directives on recycled content and whether or not those targets will have an impact on the commercials of the second use market. So there was obviously huge positive impact from it, but there are also potential unintended consequences when you're looking at, in effect, pulling out those batteries which could be used in grid energy storage applications because of the clamour to recover the materials, be able to meet those targets for the new cells being produced.
Okay, we got another question here.
In the US, they're considering putting in place basically a passport for every battery, which will tell the recycler exactly what's in it. How deep that detail will go will depend on how much the manufacturer is willing to disclose. But we know the NMCs may have niobium in them, they may have boron in them, may have bismuth, they have all these extra elements. Is anything like that being considered in Europe?
Absolutely. Yeah, no, there is a lot of work going on around a European battery passport. I don't know if anyone wants to pick up on that.
Yeah, I can just echo that. Yes, there are some works going on in that respect. We have some initiatives from European Council, some support from European Council, and here in the UK, we are collecting some data from each individual battery pack going into some of the vehicles produced here in the UK at the moment. I've seen it in the news, and you're right. In the US, they're doing it. I've seen it in the news that BYD currently collecting all potential and possible data from their battery packs. They still don't know what they're going to do with those data at the moment in 10 years' time, 5, 10 or 10 years' time. But they're collecting all of those data at the moment, and I'm sure some of those data will be very valuable. Probably some of them not, but it's an important and interesting topic, and I think digitalization and digital and data analytics will play a big role there, which is becoming more apparent and clear for the UK battery ecosystem and R&D ecosystem here in the UK.
And the second part of my question is still recycling. We all have at home and in other places a whole range of laptops, phones, and there's lots of cobalt in them. Is a consideration being forced recycling and keeping those materials in the home country rather than shipping them overseas to somewhere else?
Yeah, so it's been one of the things that have been really positive from a waste directive recently, is looking at that. So EMR as a business do quite a lot of, so it's what's called recycling, so waste electronic equipment. And a large part of that is about attempting to recover, in effect, the same black mass to get the same cobalt and nickel out of it, because as you say, consumer electronics is a huge one. The other one is looking at power tools, and with the producer responsibility that's coming in, there's becoming a huge market in the collection of secondhand like power tool batteries from household items as well as vehicles. So it's been fairly well known about the automotive side of it for a while. That's slowly going across other industries. So hopefully that will get significantly better. It also tends to be a net inflow of materials because unfortunately, for various reasons, most of those electronics are still produced in the Far East. So if we can recover those materials, in the UK, that's obviously an alternative to us directly mining those naturally and importing those ores.
I think Joe will come in there.
If I may add, it's an important point, and this is beyond technology. It's about behavior of people, and we really have to change behavior, the mindset of people joining the circular economy, and that's really the challenge. If I talk to recyclers, this is one of their key bottlenecks in getting the stuff. The behavior of people. And coming back to my concept of accessibility, that's exactly one of the 6 mechanisms that humans have to hinder, let's say, the access to minerals and metals. It's one of the 6.
Hi, Jennifer Channel from the Faraday Battery Challenge. I just wanted to pick up on that point because I had a discussion with DEFRA yesterday about this. So they're currently doing a consultation looking at the battery passport, encouraging more recovery of batteries from consumer electronics, and also looking at the extended producer responsibility with EVs. So they're currently undergoing a lot of work looking at this, and I think to date, a lot of the battery passport work has been driven by the EU, and at the moment we're looking at what the role the UK should really be playing and taking more of a kind of proactive role in the kind of battery passporting world.
So my question is related to the recycling technology. For example, there's 2 methodology available, the pyrometallurgical, which is energy intensive, and the hydrometallurgy, which is chemical intensive. So you add a lot of carbon footprint in the process. So could you think that maybe the recycling can backfire all these net zero strategies that you have?
So I'm going to start from a recycling perspective by caveating that we don't go that far ourselves at EMR. We tend to stop at black mass. but obviously as part of our process, we're working with a lot of the refiners in order to understand when we should be taking out specific target materials and how our pre-processing impacts theirs. The general trend and preference is moving towards the hydrometallurgical route. The challenge there is more about co-location of sites because of your process water. I think anything on the pyrometallurgical side will always be very energy intensive, and you'll also have a fairly high loss rate from it. It's more commercially driven, I would say, at the minute in the short term, but the trend seems to be going down the hydro route. It is also an important factor. So Role of UK BIT in Reykjavik is doing a full life cycle analysis for exactly that purpose. We can't just assume that recovering materials will be significantly better than mining virgin. We need to have numerical data to prove that, be able to demonstrate that and calculate that point to understand and confirm that that is the case as well.
Joe?
About 10 years ago, we did a study with Umicore, a recycler in Belgium, on the recycling of lithium-ion batteries. And then indeed, recycling is not for free, environmentally speaking. But in the end, it's favorable or more favorable than primary sourcing, definitely. Because yes, what you have there from a recycle perspective, it's really gold. The level of concentration compared to the mine, this is amazing. So it's not for free, but it's favorable. And of course, also their technology and change in energy mix could for sure also still improve what they're doing today.
So which potential do you see in direct recycling during production?
So there's some really interesting areas that have come out of the Relib project in the UK. I'd kind of encourage anyone to have a look at that, particularly on direct cathode recycling. So recovering straight off the copper foils and trying to feed that back rather than having to go right down to base metals. I think for anything end of life, it will tend to be cost prohibitive going that route, and also with the changing chemistries. You also need to tend to do it in very clean environments. So if it's an entirely closed loop process within the gigafactory, I say it's viable, but outside of that, it's extremely challenging, I think is probably the best way of phrasing it.
Thank you.
I've maybe got a question really for Alexander, and I think it's about investment in the sector that you're operating in. I mean, given the timescales that you discussed, how do we really convince the investment community about the potential, try to overcome their perception regarding some of the risks? You know, do you envisage more private sector investment in this area in the UK, or is there a bit of a risk of a market failure here where we might need to see more intervention from governments?
So from the recycling side, I'd say the primary recycling of receiving batteries, disassembling and shredding down to black mass is fairly well covered with a few big players in the UK. The secondary process, looking at the refining, is a huge void at the minute. That's probably the biggest challenge. I've discussed this at length with the APC as well, so I assume Hadi will have a similar view on this point. But that appears to be the big shortcoming, and you're talking in the realm of £100 million investment required to build a plant looking to refine and recover the black mass. And at the minute, there are no major players who have made large commitments in that space. Unfortunately, Johnson Matthey recently pulled out, who were probably the leader and front runner at this point in time. There are a couple of other big chemical companies and refiners who we expect to move into this space, and preliminary high-level discussions are happening, but there is a severe lack of commitment in that area specifically.
Okay, thank you. So if there's no further questions, I'm going to pass over now finally to Rogerio Ribas, who's head of battery development at CBMM, to just give his final reflections on the day and to formally close the event for us. Thank you.
Thank you all.
So, bom,
On behalf of CBMM, I would like to give a special thanks to our speakers that booked the day to be here with us despite their busy agenda. Thank you. We also would like to thank you all the participants that spend the day here with us following the presentations and also bringing questions and open some discussions. And of course, we'd like to give a special thanks to our organizers that took care of us in all the details. My evaluation, that was a very interesting day. So we start with more fundamental research, how fundamental research is important to bring new materials or to develop or to discover new materials for better application, and also to solve some problems from the current and future technologies. So in the session number 2, we could see new companies and entrepreneurs that are bringing science to technology and technology to business, which is very good. To see everything. Now we can see not only the powder, but we can also start to see cells, modules, systems, and also applications. We have all those projects that or companies that give some presentations here. There are many demonstrations that they are building, maybe because of some confidential clause they could not bring here today, but very soon we hope that we could see those demonstrations. And now in the last session we could see this important issue, which is the sustainability, recycling, and also circularity, because we know that for any new technology in the battery space we need to deal with that, otherwise it's just another idea. So it was really a great day. Thank you very much for being here. I would like to invite you for a drink reception just by side. Thank you.